you very much for the introduction. Let me also take this device and thank Andy, but also Ben, Chris, and not least Natalia for inviting me. It's always a pleasure to be here. It's a place to focus and refocus in particular on science and get things done, and also having a good exchange with international colleagues here on a topic which is partly new to me. So I do a lot of PD constraint optimization, but I'm somewhat new to the energy area, and I realized that this is a little bit out of line. It's not talking about risk aversion, although risk aversion is certainly a topic which might be worthwhile to study later on as soon as we understand those models a bit better. I realize it's gas and not energy, not electricity. This is why I was a bit careful in accepting, but finally we had not only Sarah's talk where we saw that there is a relation between gas and electricity, but also we've seen that there might be a transition period for some countries to all renewables using gas still, and for some others there might be even a longer lasting future for the gas. So in a sense it makes sense to look at gas transport, and it's a little bit out of line because you will see partial differential equations rather sooner than later. So I would like to look at the spatially but also in time sort of continuous model. Let me mention that this is joint work with Thomas Horowitz, a professor at the University of Marburg, and a former student, Adrian Kemmler, who then joined a finance company after that work. Now, the talk is mainly motivated by this graph. I mean, strictly speaking, by a portion of this graph only, obviously. But I think it's clear to everyone when I speak about gas that this is the gas network, European gas network. And when I talk about PDEs, I don't have the illusion that we'll have PDEs models for the entire system at some point in time, but I think we should rather think about a kind of multi-scale model where you have a fine-scale model in a region of interest, and then you reduce the model by various ways, for instance using physical insight into simpler and simpler models generating initial and boundary conditions further down, so to speak. And I'll focus on the fine-scale model and try to understand whether this is a feasible project in its own right, and if that works out, then I think we have some basis in order to try to march along this process. Gas is also interesting because what I show you here is a kind of energy dependence map of Europe. So we see here that there's a small number of countries which are almost autark with respect to importing energy from outside, but many others, in particular in this region here, but also here in the south, heavily depend on influx of energy from other regions like Italy, from Africa, but also here we have in Germany, for instance, gas coming from Russia mostly, and there's also some other, of course, transfer going on. So in that sense, a pipeline network will remain as an issue for transport, for transmission for some time, and the point would be now to understand its functionality from a physical point of view. But I spoke about spot markets, and I'll be a bit more detailed on this in a second, but let's just see. I mean, we have similar networks in the United States. If you wish to look about sub-networks, there are intrastate networks, for instance, highlighted here in red, and there's also interstate networks. So one is intrastate and the other one is interstate networks here in blue. So again, we have a complex network, and we should believe that there's physics going on every single arc. Of course, it's not all just bound to gas. You can also have other energy carriers like fossil, like oil, for instance, here in this graph here, where you then can again set up physics in order to model the transport there. Okay, so the motivation also is the fact that well, we have this kind of energy policies everybody knows. So in Germany, at least, nuclear is kind of out-phasing. So by the 2020s, they would like to see no longer nuclear, and by 2050, the ultimate goal would be to get rid of fossil fuels almost entirely and switch to renewables. And of course, the belief is also that in this transition period, at least, gas plays an important role. What I show you here is a kind of reserves of gas in different regions. We can see here Russia, where there's a lot going on here, and then there are other nations which still have, of course, corresponding reserves. And in that sense, it seems to be a transition full. And the other advantage of gas is, of course, its storability. So you can store it in certain ways. We've seen it could be the network as such. It could be storages. In addition, it can be distributed quite well, and it's also transportable over very long distances. In this sense, it's interesting. What is also interesting is the way that there's conversion in many ways from power to gas, gas to power, and so on. Now, what about spot markets? So something which I noticed is, well, one thing is I'm showing here the gas price, which is obviously now varying, and there's an ongoing liberalization of the gas market, which makes the pricing issue even more interesting. If we could distinguish the colors well here, then we would see that sometimes in certain countries we even have difference in prices depending on the region, like north or south in France, also in Germany. But in overall we see a certain volatility depending on various events, obviously. What is also interesting in a sense is, at least that's what I seem to have learned, is that gas and oil were companions price-wise for a long time, and what we see now is that the gas prices start a little bit, and this is what this red circle should highlight here, so that gas prices are starting to decouple somewhat from oil prices, and this is why it's worthwhile to look into the gas market in its own right and independently, because there seems to be this decoupling effect ongoing. Now, in order to give you some kind of very crude and schematic, and I apologize for the crudeness here, idea of a model, let's think about the following. You have producers. In my example, you have two producers. I think you guessed the nations here. One would be Russia, one would be Norway, but that's not the major point here. And then you have spot markets. In the spot markets, you have retailers, wholesalers that enter certain contracts, and given the contracts, then they're going to distribute, so to speak, gas. Again, it's schematic, of course. Nobody transports the gas to the spot market, so in that sense, forgive me for this crudeness here. It's also interesting to understand that producers might work as retailers themselves, so they're not just producing, but they're also retailing. And then let me just focus on one arc in order to explain a little bit what the physical model could be behind. I'll be a bit more complex in this introductory part, and then somehow reduce the model complexity in order to get a bit more mathematical insight, and then continue from there. So what we should have in mind is, well, we're talking about transporting a commodity. Of course, electricity is one instance. We would use different types of models there, but when we talk about, for instance, gas or oil, then typically we have partial differential equations, which will depend on a state. What would be the state? Typically the velocity, a density, perhaps the pressure of the quantity of interest. So gas is being compressed, so there's a variation in pressure. It's being transported, so there's a velocity, and there's also a density matter going on there. And it will be transported in space over time. So this is why I have a spatially distributed but also time-dependent model here. And following some terminology from the control community, y will be my states. So now you may say state could be velocity, pressure, and density all at once, or just velocity in case of interest. And you have controls, which could be produced volume in time, or it could be also purchased volume in time. So this is the difference between the superscripts here. And again, they are time dependent, but potentially not spatially dependent, because the assumption would be the producer plugs oil into at one end of the pipe, so to speak, and it comes out at the other end of the pipe. So there's just a time dependence, but no spatial dependence there. And of course, typically we have more than one producer, but even if you have just one producer, you should assume at least that you have more than one retailer, wholesaler. This is why we see here indexes from 0 to capital N. Okay. Now, if we talk about the gas, one aspect, of course, to understand is we don't go to a very high resolution, high fidelity model, because this would mean a 3D gas flow through a pipe, but then this is not of interest at all in this context. So the belief is, of course, that we have length to a long pipe compared to its diameter, which allows us to reduce the model to a one-dimensional model in space, but still it's time dependent. So this is why it gives rise to partial differential equations. So we see here once the derivative with respect to x, and otherwise the one with respect to time t. So x is space, t is time. And then you would see here this coupled system of equations, which gives you the transport of gas. Rho would be density, v velocity, and pi the pressure in the gas. And this would be derived from basic principles. On the right-hand side, you see two interesting quantities. H prime would be somehow the orientation of the pipes. If the pipes are perfectly horizontal, H prime may be thought to be 0. If not, then there's a kind of gravity force pushing the gas. Otherwise, there is a coefficient over there, the lambda, which is the so-called friction coefficient. What you have to have in mind now from physics, if you're pushing gas through the pipeline or to the tube, so to speak, then of course the roughness of the surface inside will determine how much you can push through, given a certain amount of time. And the friction coefficient is a quantity which we strictly don't know under operating conditions, but we did some work, for instance, where we estimated or we quantify the uncertainty in this even as a function, lambda, over time for measurements of pressure drops at the beginning and at the end of a pipe. So there is some physical uncertainty there which you can estimate given some data, but that's not the point of the talk. You see also a little term here with an epsilon. So the system without this would be what we call a hyperbolic system. Just to give you a brief idea, a hyperbolic system is like a wave-like phenomenon. So you start at some point and it takes a while until the wave reaches at another point in time. Whereas if it would be, let's say, an elliptic or parabolic phenomenon, every change in whatever data you have would have an immediate global effect, and this makes sometimes the world a bit more complicated than the hyperbolic notion. But there's a well-established regularization which is called viscosity regularization, which allows you to find the right solutions if epsilon goes to 0, and this would bring you back into kind of parabolic world. Just to mention this here because you can have then some viscosity regularized transport, and this is also a well-accepted model. This would be a kind of PD model for the gas transport, and as you can see here, there are some nonlinear terms there. There are some nonlinearities on the right-hand side, and those can partially be removed by arguments depending on what we know concerning velocity. It's not traveling awfully fast, for instance, then quadratic terms can be neglected, or you have other reasons to get rid of certain nonlinearities. For instance, if there would be perfect surfaces inside, you could reduce the friction coefficient to a very small number. Now, what else should we have in mind? So this not verifies the transport. It could be that, for instance, the state itself is constrained. So you have a lower bound and upper bound, thinking of it in a scalar way, for instance. You cannot go faster than a certain upper bound because otherwise you have technological consequences. The production, well, let's say the state, remember it's the let's say amount of volume at the entrance node, not here. If I think of just a one pipe model, I have 0 being the entrance node and 1 being the exit node. Then I have the producer's volume over time being put into the pipe at the entrance node, and I have a certain amount going out at the exit node, and this might not be less than certain contractual agreements which I denote here by UDI. So there are capital N plus 1 many agents on the market, and each of them has a kind of contractual demand to fulfill, which would be UD depending on the agent I, and this may vary over time. And then obviously there are also certain capacity bounds for the producer, so you cannot produce more than certain upper bound. Otherwise, there's also a lower bound, assuming that there is no storage where you can benefit from. So in a sense, you have either 0 production or you have a certain upper bound. Also, the retailers or wholesalers may experience certain bounds, and again, I have simple bound constraints, and it has to do a bit with certain consequences we'll discuss later. But again, for the simple model, it might be enough to believe there is no storage which you can have as a retailer, and at the same time there's an upper bound to what you can purchase, because if you exceed a certain bound, then you can't process it in a way or another. Now objectives, just very simple objectives, and again there can be way more complicated versions, but I just like to give you an idea here. So let's assume I have entered a contract, or I have agreed on a contract with a contractual amount UD, and if I don't deliver, I'm penalized by a certain amount mu naught. And here it's a simple penalty, it's just one number for all times, but this will vary of course. And this could also be an asymmetric penalty where I have a different kind of consequence whether I over or under supply in a sense. There are certain production costs which we see here integrated over time, of course, and there is certain revenue again integrated over time, and we assume here that the prices or so in a sense are exogenous, so they are given, although it might be of interest also further down in the research to have a pricing mechanism coupled to this game in its own right. And a similar story here, so this would be the producer's objective, this is the wholesaler's objective, but the idea would again be the same. And then of course the overall problem would be the producer optimizes a utility over certain controls, which would be once what the production is doing, U up or not, and secondly what the producer does as a wholesaler. And then there are private constraints, but there's also this PD constraint, because the producer has to somehow see the fact, or has to respect the fact that there is physics going on in the network, and there are these kind of state constraints as I showed it to you. And of course the wholesalers have a similar problem, so everybody utilizes their utility here, optimizes, minimizes their utility subject to certain private constraints, but again they all have to somehow respect the fact that there is physics underlying. So in a sense, the idea here is that we couple the physics to the market, so it's no longer that the market displays a kind of decoupled game, but you really have the physics brought in here in a kind of high fidelity physics because it's on a partial differential level. And then of course the question is how can we characterize equilibria, and this is of course going back to kind of Nash equilibrium conditions. So what I'll do next, and I apologize, this is something I'll do at the late hour, I'll go through some of the mathematics here and I'll try to highlight some of the dangers and pitfalls which come along from infinite dimensions, because you may ask the question at the beginning, well at the end of the day we have to solve this, which will most likely not be done analytically in infinite dimensions, but will be done by some numerical procedure. So why worry about infinite dimensions if we could just discretize, come up with the finite dimensional solver, and then well, call it a day once we have the results. I'll try to touch some of those points, and I'll make it a bit more abstract because you have seen one model there, but we can have also models where, for instance, we simplify in space but keep it time dependent. So you may have a kind of PDE where the space just becomes a kind of aggregate quantity, no longer spatially distributed, but then it's still time dependent, leading you to ordinary differential equations. And then you can also say I would like to get rid of time, which ultimately leads you to an algebraic system, but of course then you're in finite dimensions and some of the topological aspects would be gone. But in that sense it makes sense to look at an abstract GNEP at this point in time. I'll talk a bit about the extension, existence of solutions, equilibrium conditions, how to solve this, and I'll give you some first numerical results, and again be gentle and patient. So this is just something which we started recently, and more complex things have to come in case you approve what we have been doing so far. Now what do we have in mind? What we have seen is very often in the control business objectives which are of separable nature, which means you have one part of the objective where the state enters. Again, the state is the state of the underlying physics. And I also realized that I'm departing a little bit from terminology, but let me first finish my sentence here. And there's a second part where the control enters. You see the little I, which means this is the ith agent exercising its control on the common state. And then you have the corresponding pair over there, and then you have in an abstract form an operator equation which is linear. Obviously, if you take, for instance, the gas model, you have a steady state and you linearize around the steady state and you end up with a linear system which would fit into this framework here, for instance. And then we assume there's an operator on the right-hand side which acts on not just ui but also everybody else's decision. This is the u minus I. And of course, in a sense, the y here is another variable. So sometimes we don't see this in NLP or game literature that you have a distinction between one of the variables and all the other variables. But I think in the PDE world, a state is so much different from the control typically that I wish to keep this kind of distinction. But we should keep in mind that y is just yet another variable in this kind of game business. Private constraints and state constraints. I think I don't need to read out what it means to be a generalized Nash equilibrium point here. So I think that's a well-known thing, that there cannot be unilateral degrees of an objective by changing unless getting somebody else's worse off, in a sense. I have a couple of data assumptions. I think I don't go through the details here. If somebody's interested, it will be on the slides. This is why I kept it, because there's an interplay about topologies, and I would like to, let me just try to go back here, focus a little bit on the fact that, for instance, a state constraint could look similar to the constraint which we see here. So I may, for instance, require at some point in time that y should be less or equal some upper bound, pretty much as I did it somewhere, well, here is a lower bound, for instance, so there's a kind of bound constraints on y. I have a bound constraint on u. They all look similar structurally, but topologically they are completely different, and this is why I wish to focus on this, and this is also why I see some of these complicated assumptions there, which I won't go through there in detail. Well, one thing is of importance here in the PDE world. Well, let me just go through nevertheless quickly. So we talk about reflective separable Banach spaces here. Whenever you see this capital U, it's a product space having all decision spaces of the agents little I in a product space together. We talk about reflexive spaces y and w here, and another Banach space x, and I have some continuous embedding of y into x, and I'll be more explicit later on. And we have to have a kind of weak star relative compactness in x star of bounded sets. I mean, one issue here which is important is whenever I have a control acting on the right hand side, which is then somehow processed by the B, and I solve the equation, then the map should be compact. What does it mean? If I have a reflexive Banach space and I have bounded sequences, then I get usually the existence of a weakly convergent subsequence. So I just gave the notion here of weak convergence, which is in a kind of duality pairing here. So UN converges weakly to U if it does so in this duality pairing for all elements out of the dual space U star. And strong convergence is always related to the norm. Of course, we know that in finite dimensions this distinction is completely lost, because whatever converges weakly converges strongly and vice versa. But here we have a kind of one way only. If a sequence converges strongly, it does so weakly, but it does, if it converges weakly, it never converges strongly. But if you have a compact embedding, a weakly convergent sequence is mapped onto a strongly convergent sequence in the kind of image space of this compact operator. And that's why we need this kind of compact embedding here. Okay. So another interesting point, and I did a little bit of a back of an envelope computation there, is the following. If I have a constraint like the state being less or equal 1, and if I would like to write down a KKT type first order optimality condition, and everything in the world, let's assume the world would be convex here, your first answer would be existence of multiplier would depend on existence of interior points, because that's the Slater point constraint qualification. And if I write y less equal 1 almost everywhere in the sense of Lebesgue over a domain omega, so omega could be our pipe, so to speak, so that's omega, then one might be tempted to say, okay, if I take, for instance, the zero function, which is perfectly integrable, so the p power is certainly integrable, it even gives you 0, is sufficiently far away from the 1, it's an interior point. The answer is this is not true in general. If p is not infinity, you can come up with this kind of evil functions which have a very small norm in LP, but they have a huge spike, but it's just supported on a very narrow set. So then they would have a very small norm, but a huge spike, and that huge spike will always violate the 1 bound. So you should not believe that if a function looks particularly far away from 1, that it would also be an interior point, because it very much depends on the topology, on the unit ball of, or on the balls of that topology. Obviously, if I go from p to p from p below infinity to p equals infinity, then such a behavior cannot happen. So if I'm epsilon small in L infinity, then I'll be far away from the 1 typically. Okay. And this is what this story should tell you, because at some point in time you're solving partial differential equations, and you cannot just come up with a wish list, because you may say, aha, now what I learned from this remark here is I should pose my problem in L infinity. And that might be possible, but it's not that you can come up with a wish list, which then comes true at the end of the day, because you have to solve a PDE. So the PDE analysis should not tell you whether you can get into such an L infinity topology by embedding or not. And this slide tells you, well, in certain cases you can't guarantee this. You have a certain regularity theory going on, and if, for instance, you're in a certain Sobolev space W1b, I don't go into the details, then there's an embedding theory, and embedding theory tells you now I'm in L infinity. And if I'm in L infinity, then I have existence of an interior point as a postulate here for the constraint set K with respect to the states. Okay, so this is an interplay, so there's not necessarily a wish list. But now you may say, aha, what does it matter? If I discretize, I'm immediately in Rn, and I immediately have an interior point. Well, this is fine, and that is true, but now at some point in time you wish to get closer and closer to the infinite dimensional model, you would refine your discretization. You will always have an interior point, no matter how fine you will be, but just in the limit you won't. Well, how does it feel in an algorithm? Well, your multipliers start to explode at some point in time, and your solver may not get anywhere on sufficiently fine meshes. So this is a consequence of not respecting those topologies here. Okay, and then there are some other assumptions which I don't go into the detail. Let's assume constraints, so the private constraints are unsuspicious, non-empty convex bounded sets and closed. And also the objectives are well, convex completely continuous have certain properties, but they don't pose any difficulties here in their own right, so to speak. Well, then what we do very often in this context is, since we have isolated the state from the controls, there must be a reason for that, and the reason is typically given the controls, which means the decision of everybody in a sense, so the wholesalers, but also the producers, I can solve the PDE, the solution operator is S, and I can reduce the problem to be a problem in these decision variables only. So now the state is gone, and we are back to more, let's say notationally, we are back to having just UIs there. The Y is more or less hidden in this S notation to the solution of the PDE. Well, and then we call a point U feasible if it satisfies, so if the vector U satisfies all constraints, the private constraints and the PDE is solved. This is what the S of U does, and the resulting state is feasible with respect to the state constraint. So this is somehow this feasible set. And by the assumptions which I have a system now which is a game where each problem is a convex problem, so this is why I call it a jointly convex generalized Nash equilibrium problem. And have written down again in mathematical terms what it means for a feasible point U bar to be a Nash equilibrium, now written down in terms of what I call here this curly J here, which is the reduced objective, which no longer depends explicitly on Y, but implicitly through the solution process. And there are examples which I don't explain in detail. Now, what are the difficulties? Well, we would like to understand if we come up with such a model whether it has a chance to survive in the sense that there is existence of an equilibrium, because if that's not true, then I would somehow get rid of my model and have to either find a different model or a different strategy. And the issue here really is about topologies, because we cannot have strong convergences but only weak convergences, and so we have to resort to weak topology, but nevertheless can apply fixed point theorems like the one by Kifano or Kakutani. Equilibria, well, we are able to prove existence of a Nash equilibrium, but this is mostly done by resorting to variational equilibria, proving that there exists a variational equilibrium, and then conclude that hence exists also a Nash equilibrium. Numerically also complicated, because we get a large-scale problem. We need to argue how we handle state constraints, because the point is numerically our desire is to come up with what I call a mesh-independent solver. Which doesn't mean we do not discretize, we will very well discretize, but mesh independence means that on fine or sufficiently fine meshes, the solver may get more expensive per iteration, but the number of iterations starting from more or less the same starting point will not increase as you refine the meshes. Of course, every iteration has to get more expensive because the discrete instances get larger. If you have a solver which has an increasing number of iterations, well, then you have mesh dependence, and this is a bit unwanted, because as you refine the discretization, number of iterations increases, and ultimately you have no solver for the infinite dimensional problem, which is an issue in its own right, but at some point in time on fine meshes you cannot wait long enough to get an epsilon good solution. This is why we do a kind of regularization of the indicator function of the state constraints in the spirit of Moreau and Yoshida, which gives you parameter dependence and a Moreau-Yoshida path, and then we still need to conclude on whether we have found an equilibrium or not, and this is decided upon by using the Nikaido Isoda function, which allows us to conclude whether we are at the Nash equilibrium or not. These are the strategies. Okay, I have also pointed a little bit to the literature. In finite dimensions, of course, there's a lot. I just mentioned a few names here. Of course, there are many, many more. The usual apology is worthwhile being mentioned here. In infinite dimensions, it's different. In infinite dimensions, games have not been looked at that often. There is some work, but sometimes sort of not complete, or just touching a problem which then turns out to be just a monotone variational inequality, and hence a somewhat simpler problem to be solved. Now, how would we characterize a Nash equilibrium? Now let's assume for the time being there would exist one which satisfies an interior point condition here. I'll tell you in a second what that means. Then you can write down first order conditions. So what you see is just a KKT system. You see here subdifferentials for the indicators of the corresponding feasible sets, and you see subdifferential for the pieces and parts of the objective function, because there was no way assuming differentiability at some point in time. If you see a star attached to this operator, this means so this is the adjoint operator, A star, and A minus star means the solution of an adjoint equation. So in matrix words, it would be like inverse intertranspose of a matrix. It's a bit more delicate in PDEs though. So if there is such a point, then you get the characterization. Let's quickly look at the constraint qualification. This is the typical Slater constraint qualification, which means in practice that every individual agent is powerful enough, so to speak, to pull the whole state into the interior of the feasible set, which is quite a lot to ask for in a sense, but that's what you need as a constraint qualification for this to hold true in this context. And also conversely, if you have existence and there's a satisfaction of such a first order condition, then you end up with a Nash equilibrium. So we have to talk about existence briefly. And this will be done by introducing Nikaido Isoda. I think this is well known to the community here. This is why I can be quick. So this is the just common Nikaido Isoda function here, the difference of the objectives. Then you define this value function V, which is the max of this psi here with respect to the second component V over all feasible pairs given the U minus I. And then a first observation is I can always choose V equals U, which means then I get the 0 there by definition of the function, so which means if I maximize the V of U will always be greater or equal 0. And there's a characterization saying it's only if and only if it is 0 for a feasible point, then I have reached a Nash equilibrium, and that's what we're targeting now. Now, I said through variational equilibria. Let me briefly remind us what a variational equilibrium is. For a jointly convex GNEP, we have this concept available, and I've written it down here again. It looks kind of similar, except for the fact that we are replugging into the V, now noted by V hat, the R hat, which is the arg max with respect to the second component of this Nikaido Isoda function. And otherwise, the conclusion is for a feasible point with V hat being 0, I have a variational equilibrium if and only if. And then it turns out that with this notation R hat here, again, a solution of this maximization problem here, I can set this whole thing up as a fixed point equation of this specific type, and then I can use Kakutani and weak topologies. Obviously, I don't have the time to go into the details here, but I'm happy to talk about this to conclude that there exists a variational equilibrium, and variational equilibria, Nash equilibrium, hence we have existence of a Nash equilibrium. Okay, and this is now in infinite dimensions. For variational equilibria, first order conditions can be weakened a little bit. So if you look at the first order at the constraint qualification here, what it means no longer that the individual has to be strong enough, so to speak, to push the state into the feasible into the interior of the constraint set K. It just means the overall effort has to be of that kind, which is a certain weaker condition as the one which we've seen before. And also, as we know it from variational equilibria, something gets a bit more unified, which is the Lagrangian multiplier related to the state constraint here. It used to be, let me quickly go back, a mu I over there. I didn't point this out, but now all mu I bars are the same, and we see just a mu bar popping up. Okay. So, and then there is a way to relax the state constraints. I think I don't go through the details in the interest of time. So what we have to get rid of, the constraint y being in K, the beta y may be thought of as being a Moro-Yoshida regularization of the indicator of IK, which we've seen before. Instead of, remember here we had the subdifferential of the indicator of K, now we see the B prime. This would be now the derivative of the Moro-Yoshida regularization, which is Lipschitz continuous as E1. So this is a differentiable object. But now we have introduced the parameter, and now we have a path to follow that, induced by that parameter, and that's what we then do numerically. And we then, of course, do some further investigation. What do we know about that path? It's bounded. There's certain weak and strong weak convergences in primal and dual space as the path parameter goes to its extreme. So there's a kind of consistency in function space. And then we have various ways to play games here. Number one is we have a semi-smooth Newton method, which is mesh independent, which can solve certain sub-problems. We can use inexact path following techniques, so we don't need to solve path problems exactly as we are far away from the limit behavior of the parameter. And as we're discretizing, this is obviously a different problem which I'm showing up here, but what this should indicate is that we also try to optimize discretization in a way that we come up with error estimators, which should do the following. Given a certain desired accuracy, you would like to throw in the smallest number of grid points so that you still can get a solution with a desired accuracy. This also can be done, and this reduces the overall effort. Let me perhaps switch to some numerical results at the end. So I'm coming back to this little spot market model, to a very simple spot market model on a single arc. I replace the gas by a transport regularized by viscosity, as I explained earlier. Otherwise, you see all the same constraint as we discussed them earlier. So we have this kind of production side, we have this kind of demand satisfaction, we have the constraint that on the exit node, the Y should deliver what is needed. And we have also some initial condition in time over space. This is a kind of initial state in the network, and otherwise it's the same problem as you've seen it before with certain quadratic objectives and the cost functions as I explained it earlier. Certain model parameters, perhaps no time to go into in details, but what you see here is how the parameter gamma is automatically updated by a sensitivity-based scheme. So we don't do it by hand, we don't just multiply by 2, 10 or some multiple. So we have a kind of sensitivity-based increase which shall do the following. If there's a strong change in the Nikaido Isoda function, depending on this gamma, then you're very careful with the update, and otherwise you're a bit more aggressive, and that's what you see towards the end of the iteration. You're going to be a bit more aggressive in updating, whereas you're more careful at the beginning. Well, this is an example of one pipe. What you see here is the evolution of the state Y. Remember, that's the transported quantity in space. This would be the pipe, and this would be over time. And what I didn't reveal here, we have a demand which is periodic. So let's assume you have a kind of periodic demand which is pre-given. And then you see what we discussed the other day, this kind of line packing or line filling ahead of time. So you anticipate that something is coming along in your desired state, and this is why I already fill, so to speak, the pipe in order to have available at the time what you need in order to deliver or minimize your objectives. Well, there are some other aspects which we studied, convergence rates, perhaps not so much of interest here, but of course you're interested what is the convergence behavior of the solver with respect to the parameters gamma which we introduced, but also with respect to refinement of discretizations. And what we found out, of course, that you really see, given this kind of periodic demand, the strategic behavior of the producers by filling the lines, so to speak, and also the wholesalers already in periods of low demand. You're already filling the line in order to have available what you need in periods of high demand. And this is also, I think, where the gas network can be used as a storage in the sense of what Sarah showed earlier this week. Well, this was a kind of first attempt. Many things need to be done, at least from my point of view. I mean, one thing is this kind of multi-scale notion and idea to connect to many things which I have seen earlier this week. But also within this model, this fine-scale model, there are many things to discuss. Let me just mention number one. We have taken prices as they are, but they really need to be computed on a market. So in a sense, there's a kind of equilibrium model there, which may have its own uncertainties, and so this would ultimately give rise to a MOPAC with PD type of constraints. Of course, there are many other uncertainties. One uncertainty comes from the market, another one uncertainty may come from the physics. So I mentioned this friction coefficient is typically not known under operations, so you need to estimate it, but estimation can only be done up to some uncertainties, and so you better know what those uncertainties are. I was considering a passive network, because if you think about an active network, there's compression going on, and turning on and off compression would be a 0-1 variable, so it's really kind of mixed integer PD constraint optimization or Nash equilibrium problem, and so on. Of course, having said this, we need to improve our algorithmic features. Then another very important aspect is closed loop versus open loop. Andy and I had a long discussion yesterday at lunch. What you saw here is an open loop control, which might be fine for short time horizons, and you may also think about receding horizons where open loop controls are somehow concatenated if you wish. But of course, as much as we don't fly from New York from London to New York by setting the flight path in London and never touch it again, we are not deciding on a strategy in such a gas network at hour 0 and let it flow over time. We would somehow revisit the state of the system, feed it back into the control mechanism, and that's what closes the loop and gives rise to a closed loop control, which makes this project even more complicated. And then, of course, I have given you some parabolic regularization. The real system is of hyperbolic nature, which has its own difficulties and tragedies, and this would, of course, also complicate, and is something which we're currently looking at. And of course, I realize there are many other aspects which we should discuss, and if there are any suggestions, we'll be more than happy to take those. Otherwise, just a quick summary, which I don't read out, but what I do want to do is I would like to point you to this kind of collaborative research grant which we have in Germany on mathematical modeling, simulation, optimization using the example of gas networks. So it tries to come up with this kind of model hierarchy from combinatorial to PD-based models and try to combine those. And also within the new cluster of excellence in Berlin, we have energy and markets, and there's a lot going on in the future. So if you're interested, I'm happy to discuss. Thank you very much for your attention.
So, thank you, Michael. I think this is very educational. I certainly learned a lot about from the talk. So I have a few technical questions, and then the audience can jump in later on. So first, a rather simple, sort of innocent. I like to pick up typos, so maybe I'm trying to.
I just thought the innocent questions are always the more dangerous ones.
I'm trying to understand what is GNEP.
That's a typo.
Okay.
Well, that was easy. That was a typo.
Okay. So when you describe
one question.
Okay, I'm done. Okay.
So sorry for this.
Okay. Yeah. Anyway. Okay. So in the model that you mentioned about this gas transmission, somehow I don't see you have the production cost and then other costs, but somehow the transmission cost is not in there.
Yes, I agree. So I should have mentioned this that let's say the system or the network operator is not modeled yet, but that's certainly an aspect in its own right. So I should have mentioned this. It's not part of the model, but it's part of our thoughts certainly that it should be part of the modeling aspect there as well.
The cost of transmission.
Yeah. I agree. I fully agree.
Okay. So thank you. So can I? This
one
is
more.
Oh, one more. Okay. So I'll pick an easy one. So when in the reduced model, right, when you substitute out the y variable using the state the control variables, don't you still need some kind of convexity in the individual players' variables to prove all those results?
It's a very good point. I mean, of course, I did have convexity because I had a linear operator equation. Remember, I said AY equals BU. And there was the PU was written maybe in a strange way, but when okay, now let me just go back.
Okay, so you do
here. This is linear. This is why I said it's a linear operator equation.
Right.
So which means if I resolve, there's a linear operator a minus 1b, which has to have properties, but otherwise it's linear. So which means everything else is convex, then this reduction process would still
be. You
be.
have with b as a function of u, right? So why is that linear in U?
B is a linear operator.
B is a linear operator.
It's just a linear operator. So this makes it linear.
Okay.
And this is also why, for instance, transiting from this to a PDE model where you have, let's say, a semi-linear nonlinearity, which is perfectly well understood as a standalone object, so to speak. It could be monotone, you have existence and everything. As soon as I would plug in such a innocently looking nonlinearity and I do the reduction process, I end up with a non-convex problem, and this makes it a bit more delicate because Kifan-Kakutani is out of reach then. There's a few things you can do, but in general it's much more delicate.
Okay.
So here benefit.
So I missed the linearity part.
Yeah, it looks a bit non-linear there, but it's just meant to indicate the vector ui and u minus I, but it was linear operators.
Anyone else have any questions, Edie?
So, in this arrangement, what you're really interested in is looking at a situation where your the contracts the requirements to meet the demand are specified up front, and the players are in a sense competing to solve that. But I'm assuming that probably those contracts are pushed to be the maximum in some sense that can be easily met by the system. There will be an economic advantage to pushing contracts in a way which stretches the gas transportation network. Do you have any because if those are to be chosen by the players at some point, as well as the detailed transportation things, would you expect that to produce maybe a rather difficult to solve system?
I'm not sure whether I understand the question completely. So
The U's here
Yeah.
are the controls.
They're the
but-
controls,
but,
yeah.
they respect the contract, like in the example you showed,
Mm.
the demand,
yeah,
that was given in advance, isn't it? And we're trying to meet that.
that is given in advance. Yeah,
Yeah.
Mhm.
So that demand is a contractual arrangements that have been made
Indeed.
in
Yeah.
advance.
Mhm.
And I'm guessing that those contractual arrangements would typically
Yeah.
be made in a way which achieve, economically we could expect those to push the bounds of the transportation network. We're going to want to transport as much as possible.
Yeah, I mean that depends on how you set the UDs. I mean, in a sense, if they're preset in a specific way, it would not change. Let's say, would not make it more complicated in a sense.
No, this is not a question about complication.
Yeah,
This is
yeah.
a question about whether we could expect to see problems in solving the PDE's framework because of the nature of where we're likely to be operating these systems.
Well, of course, in general, yes, I would say. I mean, in this specific model, it perhaps is ruled out by the way how I reduce the system and how I rule out certain specific switches or so. But of course, it could be that you may somehow get to some limits of the system by the way how the agents behave according to the demands, and that might be true. For instance, that you reach certain constraints and then you may run into difficulties. I mean, mathematically, as soon as you satisfy the prerequisites, all is fine. But I agree. So I mean, there could be states of the system which may be complicated in case. But then you have a system operator. I don't know how those would act here in the real world. If they regulate, then they can somehow help to regulate certain complicated situations and counteract. But otherwise, yes, there might be difficult.
Is the gas network run by a system operator like the electricity transmission network? I mean, this is kind of
That's not.
arranges the transport, or
No, well, I think that's not that might not be the case. No, in general.
you just push stuff in and hope.
I mean, there are some. Of course, there is some system operator because you need to compress, for instance, every once in a while. In that sense, there is, and I think there are gas companies that run the network, so to speak. In that sense, there is a system operator. Yeah.
So in electricity, the system operator takes care of all these laws of physics, which would give you a generalized Nash equilibrium problem. If you
Yeah,
context.
I
So I'm wondering whether there's a way of
Yeah, here you might have something like this, but it's more like operating. I think it's more like operating the transportation as such, but not optimizing in a sense of a Nash equilibrium. So it's that you have people running the let's say the compressors according to certain let's say interpolation curves from data or so, but they wouldn't operate strategically as optimizing some sort of game there. I think that's not what they do.
I think that what Eddie was saying is related to a question that I had asked you. If there is a congestion in the network, then you will not have some interior solution, or maybe some constraint qualification will not hold, right?
Yeah, but
This
that
may be a problem.
I agree. But at that point in time, this would not somehow endanger the functionality of the network. And whatever congestion means, of course, if the pipe is broken, well, you know. But the point is, otherwise, you don't have existence of a multiplier, so it's very difficult to find a Nash equilibrium. If that's what you mean, then this might well be the case. But in general, yeah, I would not assume that this is an issue.
How important is the assumption that you're finding variation in equilibrium
It's a way of proof here. I mean, in a sense, it doesn't need to be necessarily. It's just a pathway which we found in order to prove that there exists Nash. But otherwise, it's not a major limitation here. So.
I'm not sure if this is a relevant question, but let's say in the electricity market, we sort of have markets like financial transmission-wise,
Yeah.
where we say these are feasible sets of flows, and then we try to create property rights,
Yeah.
and we sell them. So I was wondering what would be the natural type of property rights that you would get here in the gas sector, because what we have now is sort of property rights where you have to be within a certain band over a day, sort of integrated
Yeah.
flow constraints. But what do you get out of your your simulation, do you have also like a feasible set that you could decentralize with products for transport, let's say?
Yeah, I mean, of course, you get. You get a few things out here. I mean, one is of course the plan for each agent, if that's one point. I mean, and that gives you. I'm not sure whether I understand you correctly.
Also,
but
the financial transmission rights, they help you to, let's say, hedge risk over
Yeah.
transmission.
yeah.
And you can have auctions on those things. So, and then you try to define like a nice feasible set.
Okay.
And the question is there sort of a good feasible set or like bundling of certain flows that you say over the whole day?
Yeah. I mean, I mean, I haven't seen it in this context, but these are certain things which you can think of. Certainly, I mean, I would assume that you can. So if you're asking for feasible strategies of the agents ahead of time, or
Yeah, maybe we can discuss
Yeah.
this later. I mean,
yeah. So
probably-
I'm not so familiar with electricity markets, honestly speaking. But of course, if you, I mean, the question is, what do you mean by feasible set here?
No, let's discuss
Yeah,
it. Otherwise,
okay.
it's going to. Yeah.
Yeah.
Okay, I think we'll probably draw it to a close. It's,
Can I just talk about the end thing?
oh yes, so Golden has an announcement to make.
Yeah, sorry about this. I was supposed to do that after my talk. I forgot. So, Henry's section of Informs is going to be inviting folks to submit papers for the Best Paper Award. And if it's okay, I'd like to distribute that to this as well. So please keep an eye out for it. I think there's been some very nice talks.
So let's finish by thanking Michael and all the other speakers for